Okay, good morning, Year 12 Further Mathematicians. A few more sub-chapters still left in Chapter 11. We're at 11.9, the Trapezium rule. This sub-chapter actually is pretty straightforward. It's a chapter which even single mathematicians like, because it's very methodical, there's not much that can go wrong, and there's not much thinking either. You just type in stuff into your calculator. And it's also a topic which was studied by some of you in the FSMQ. We actually did this in the FSMQ last year, if you were in my class, and yeah, it is not too bad. Okay, so the learning objective is to apply the trapezium rule to estimate the area beneath a curve. So we've just been doing integration, but finding exact areas underneath the curve, and the trapezium rule is used just to estimate the area beneath the curve. You might have an integration which you can't actually do, and you have to use some estimation method, and trapezium rule is one of those. So let's see, imagine now we've got a curve like so, call it f of x. I want to work out the area underneath that curve, but I can't integrate it. But one estimation I could do is use trapeziums and effectively split this diagram into different strips of exactly the same width. Keep that going until I get to the last strip. Okay, so these are different strips of exactly the same width all the way along from A to B. And then this first strip, I've got a trapezium there. Okay, so that's straight line, straight line, straight line, that diagonal line. I work out the area of that. Then I work out the area of this one next door to it. And then the area of this one next door to it. And so on, and the final area there. And these trapeziums, I add up all of their areas, and that gives me an estimation of the area under the curve. Obviously it's not going to be perfect, as you can see, there's bits missing. But you can get it pretty accurate if you use a few key things. Now, one of the things you definitely need to know is the width of these strips. They'll need to be exactly the same, and the letter they use for the width is h. So the width of all of these is h. And then the other things you need to know are like how tall these trapeziums are. And the only thing that's a little bit challenging is this notation, which this first height they call y0, then y1, then y2, y3, all the way up, and then the last y would be, well, let's say we had n strips, so n number of strips, the last one would be yn, and the penultimate one would be yn minus 1. Okay, and then you got the trapeziums in between. And the trapezium rule just says you add these up. Okay, but rather than do them all separately, one at a time, it can be summarized into this rule, which is integrating between a and b, some function or any function with respect to x is approximately equal to a half times h. Remember, h was the width of the trapeziums, and in brackets you got these y0, so like the heights of the trapeziums or how tall they were. So y0 plus yn, the first one, plus the last one, plus twice y1 plus y2 plus dot 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 all up to yn minus 1, the penultimate one. So it's approximately half h brackets first term or first height plus the last height plus twice the rest. And that's pretty much it. And this is given in the formula booklet. Okay, so you don't have to memorize this. You just have to know it's in the formula booklet. And the only thing which I'll remind you of is what h would be. So h is how wide the strips are. So width, b and a I've labelled on the diagram, and n represents the number of strips. or the number of trapezia, if you want to be very fancy. Okay, there's a couple of facts now you need to know about the trapezium rule. 4 of them, in fact. And one of them is how to make the estimation more accurate. So if you want to make the estimation closer and closer to the exact value, what do you think you would do? Well, it would be increase the number of strips or trapezia to make the estimation more accurate. That's one fact you need to know. Second and third fact is what would happen if you had a overestimate or underestimate. Okay, so we're going to consider a concave function. That was a fancy definition for concave function, which you should know from a previous chapter, but pretty much it's a function which looks like a cave, and a cave for me would be something like this. Okay, if I had to use the trapezium rule on this type of curve, then I want to know if it's going to produce an overestimate or an underestimate. And if I just added some random strips like so, might be easier for you to decide. Put the trapeziums in. Those trapeziums are all below this curve, so the area is going to be an underestimate. So concave functions produce a underestimate, and then the opposite for convex. So convex curves or functions produce an overestimate. And the fourth fact is sometimes you can actually work out the integration. So trapezium rule, the main use of it is to work out the area of curves you can't integrate. But sometimes they can ask you to work out the actual integral, but then also use an estimation. So do 2 different things, the actual one and the estimation. And when they ask you to do that, they ask you to work out something called percentage error, like how far your estimate was out. So a formula for percentage error is something which you've done previously, and it is the difference between the actual value and the estimated value over the exact value times by 100. So you might have to use that formula at some point in the exercise. Okay, and these 4 facts, normally they would be part B's and part C's of trapezium rule questions, maybe 1 or 2 marks each one. Right, let's see what an example would actually look like. So easy number 1. We're going to use the trapezium rule with 4 strips to estimate the area I've labelled R, and the curve we've got is y is equal to square root of 1 plus tan x. So, okay, let's split this up then into the 4 different strips. Now I've got the sketch. Okay, now I want to work out the width of these strips, and there's so many ways to do this. I'm going to try and show you the easiest way. So let's organize everything in a table, because your calculator can do this for you as a table. Because if I chose the table function, which is 7 for me, f of x is my function, my curve. Square root of 1 plus tan x, like so. Start is where I'm going to start at, which is 0. This is going to be where I'm going to end at, which is pi by 3. So shift pi over 3. My step now is what I'm going to go up in. So there's a way to work out that step, which was in the formula. Okay, so the step is this width. B minus A over the number of strips. B minus A over the number of strips. So pi by 3 subtract 0 over the number of strips. So in this case, H would be pi by 3 subtract 0 over the number of strips, which is pi by 12. So that would go up in pi by 12 each time. So I would have pi by 12, add another pi by 12 would be pi by 6, and add another pi by 12, pi by 4. Okay, and that would be it. So my step needs to be pi by 12. I get this table. And this is a table I'm actually going to copy out as part of my workings. So you get x values going down. I'm going to write them as a row rather than a column. So the x values would be 0. This is the decimal version of pi by 12. This is the decimal version of pi by 6. Decimal version of pi by 4. And finally the decimal version of pi by 3. And then, what are these f of x values? What do you think they're giving you? What was the purpose of writing this in the table? And these would be giving you your y values, your y0s, y1, y2, y3, and y4. The things which you are going to need in the formula. So they are, remember we're going to give our answer to 4SF. So whatever these are, I need to write them to better than 4SF. So the first one's the easiest, 1. So 1. Then this one, scroll down, is 1.12603. 1.12603. Next one is 1.25592. Round up to a 3. 1.41421. And the last one is 1.65289. I get this table, and it gives me all of the x values and then the height of these trapezius. The height of the trapezius. And now I'll be looking at my formula booklet, and I'd have this formula. State this formula. It says if I integrate some function f of x with respect to x between 0 and pi by 3, it is approximately half h, so half times the width of the trapezia, which is pi by 12, brackets, the first height plus the last height, first plus the last, plus twice the rest of them. Let's move that 4 up a bit further, plus 2 lots of the rest of them, which are these in the middle. So 1.12603 plus 1.25593 plus 1.41421. Close that off, and then you type that into your calculator and round it to 4SF. Yeah, there's not a shortcut to this, you do just have to type it in. So 1 plus 1.65289 plus 2 lots of 1.12603 plus 25593 plus 1.41421. Just check to see if I actually wrote the times by 2 in. I can't remember if I did. Yes, I did. Okay. To give you 1.341 to 4SF. Pretty much that would be it. So no complicated integration at all. It was all stuff on the calculator. A couple of things I had to work out was this this strip width. Once I worked that out, that would be my x values. And then use the table function on the calculator to work out the y values. And then everything is substituted in the formula, which is given to you in the formula booklet. I can kind of use my the integration button on the calculator to check my answer, because I know it's an estimate, so it should be relatively close. So the real answer will be a little bit different to 1.341, but I can see how close it is. Because if it was out by a lot, then I might have done something wrong. So 0 pi by 3, make sure your calculator's in radian mode. 1.337. So yeah, I'm happy that, yeah, this is an estimation, it's close to it, so I've probably done something right. And that would be it. So I would like you to try some questions from the textbook. I think which ones. So we're looking at exercise 11I, which starts on page 319. And I would like you to do just the evens only. Just even numbered questions only. Post your workings on class notebook. Post any questions on Teams, and have a good day.